In the last section, we talked about splitting up a picture of an area into infinitely many, infinitely thin rectangles, write an expression for the area of each rectangle, and using an integral to add them up. Well, in this chapter, we're going to do something similar, except we're going to imagine slicing a 3D object into infinitely many, infinitely thin slices. We're going to find the volume of each slice by multiplying the area of its face by the thickness, and then add up the volumes of all those slices to find the volume of the entire solid. The reason that works is because, like area, it's legit to split up a volume into the volumes of a bunch of different chunks of it, and you can add all those volumes together to get the volume of a whole. So we say volume is additive, just like area is additive. That was one of your big takeaways from geometry. So just to start to get the idea of what this is going to look like, imagine a roll of quarters. If you found the area of the face of one quarter and multiplied it by the thickness of the quarter, that would give you the volume of that quarter. And you could add up the volume of all 40 quarters in the roll, and that would be the same as the volume of the entire roll. So make the connection now to why calculus was invented. We could just find the area of one of those quarters and multiply by the height of the whole stack, and that again would give us the volume of the stack. So why bother adding up the volumes of all of those? Well, the same reason, remember, when we wanted to find the distance traveled by an object, by something that's moving, we used to, if we thought the volume was constant, if we thought the velocity was constant, just multiply velocity times time traveled. But once we decide the velocity might not be constant anymore, we're going to multiply velocity times a very tiny change in time, and then multiply the next velocity by the next tiny change in time, and keep adding up those products until we get the area under the velocity curve. So here we can use the integration if the area of every slice isn't the same. So I'm going to imagine slicing up into infinitely many, infinitely thin slices. For each slice, I'll multiply the area of the slice by the thickness and add those up, and I'll use an integral to do that. So this is going to be our technique. It works anytime you can slice a solid so that the slices all have the same shape. They don't have to have the same size, but they have to have something that you can use one formula for. You can use one formula to describe the shape. So when this shows up on the AP test, they'll be very clear about what that shape is. So that's not going to be the issue. It's just going to be to write the formula for that area. So if you want to find the volume of a solid, we're going to just assume we're going to integrate with respect to x. You're going to integrate from the leftmost x to the rightmost x. The area of a face of the slice, so what the very thin slice would look like if you just looked at it face on, we'll multiply by the thickness, but the thickness is going to become so small, it's going to become infinitely small. That's going to be our dx. So we're going to integrate from left to right, the area as a function of x times the thickness, which is our dx. So if you want that broken up into steps, these are the steps I use. See if you can sketch the solid and what one slice looks like. See if you can find a formula for the area of the slice. That's going to be some function that you remember from geometry. It's not usually a complicated one. We need the limits, which aren't usually the trick here, and then we're going to integrate to find volume. So here I have a parabola on its side, right? This is the graph of the square root of x. And I want to find the volume of the shape you would get if you took this region, which is labeled R, and you sliced it so that every slice, if you slice perpendicular to the x-axis, looks like a square, but a square with thickness. So whenever you see something a problem that says slices or like squares, I want you to think about Kraft cheese slices because they look like a square, but they do have a thickness. So you could find the volume of a Kraft single. You would need to know the side. You would square the side to find the area of the face, and you would multiply that area by the thickness of the slice. So that's what's going on here. I'm going to use orange to sort of drive home that this is going to be a cheese slice. So notice my slice that I just made is perpendicular to the x-axis. They won't mess around with you on the AP test. They'll tell you exactly which way you should slice and exactly what shape the slices make. So imagine that slice is like a square that sticks up out of the picture. So what do I need in order to integrate? I'm going to need an expression in terms of x for the area of that square. So this is what I think. I'm going to integrate from left to right. So that's x equals 0. I was told up until x equals 4. So that part's not tricky. I'm going to integrate from 0 to 4. And what I want to add up are infinitely many volumes. And volume is found, well, for shapes like this, right? We're going to pretend that every slice is exactly a square, but a square with thickness. So the way we find the area of a prism, every shape we cut is going to be a kind of prism. And you find the volume of a prism by finding the area of the base and multiplying by the thickness. The thickness is going to be our dx. So it's going to be our job to find a function a of x to give the area of the face of the slice that happens at the place where, x spaces over from 0. So I have to think about how do I find the area of a square. This is just my thought process here. You wouldn't have to write this on the test, but I want you to understand what my thinking is here. So I'm going to integrate from 0 to 4. How do you find the area of a square? You take the side of the square and you square it. So that's pretty good if you got this far. But notice I have 2 variables in my integral, so I know I can't integrate. I have to figure out how to write an expression for the side. The first time I drew it in orange. I'm just going to color over it in blue so you know exactly which piece I'm talking about. I need an expression for the length of that vertical blue line segment. Well, I can figure that out because I can see that the top of the line segment is always going to be on this curve y equals square root of x. The bottom is always going to be the x-axis, which is y equals 0. So now I'm going to be able to write my integral. All right, my integral is going to be the integral from 0 to 4 side squared dx. That part hasn't changed. But now I can write an expression for the side of my square. So it's square root of x, which was the top curve, minus 0. Well, that's pretty good. No, you have no obligation to write in the minus 0, right? So it's going to be the integral from 0 to 4 square root of x squared dx, which again, I could simplify. That's from 0 to 4. Square root of x squared is x dx. So once you've written, you could write any one of those integrals and get full credit on the AP test for writing the integral. This happens to be a no calculator problem, so I'm going to keep going. She's going to need an antiderivative for x. Well, that's not so bad. X squared over 2, evaluated from 0 to 4, which is going to be 16 over 2 minus 0 over 2. Has a volume of 8 cubic units. We saw this picture back in 7.2 when we found the area of the region R. This time we've been told R is the base of a solid, and every time we slice through this solid perpendicular to the x-axis, the cross-section has a face that's a square. Remember, it's a square with thickness, so like a cheese slice. So can I write, but I do not have to evaluate an integral expression for the volume of this solid. So I'm going to change to orange, as these squares make me think of cheese slices. Ooh, not very perpendicular. Wow. Okay. Not an awesome slice. Let me try one more time. I think I can do this. Okay, so when the cut that my knife makes into the base of this solid looks like that vertical line, and I want to imagine a square sticking up out of that base. It has a face that's a square. It's a square with thickness. So I'm going to find a way to write an expression for the volume of that slice. I'm going to add up all the slices, all the volumes of the slices. And when I add volume to volume to volume, I get the total volume of this solid. It must be like a cheese log or something. All right, so I'm going to integrate from left to right. So it's pretty clear here from the picture. It won't always be clear from the picture. Here it's clear that I'm going to integrate from x equals 0 to x equals 2. I'm going to need an expression for the area of the face of the square. And I'm going to need, just to remember that the thickness of the cheese slice, I'm going to imagine those slices getting thinner and thinner and thinner. So my thickness is going to be essentially infinitely thin. So that's going to be my dx. So the tricky part here, if there's a tricky part, I have to figure out that the area of a square comes from finding one side and squaring it. Well, here's one side of my square, and I can tell that distance because if I make those slices, if I drew in all the slices, the top of that slice, the top of that vertical line segment I'm drawing always hits the G curve, and the bottom always touches the F curve. So the side of this square is always given by the difference between the G function and the F function. So this is what I'm going to write. Where is it? Okay. There we go. So I need to integrate from 0 to 2, an expression for the area of the face of the slice times the thickness of the slice. So that's a of x times dx. I know for a square, the area comes from squaring the side, so I'm going to have to figure out an expression for s. The reason I can't stop here is because this has two variables in it. I have s's and x's. I have to get to the place where I only have x. It's my job to write an expression for the side of the square in terms of x, and I can figure out that that's g of x. Where's my pen? G of x minus f of x, so that's top minus bottom. Make sure the whole thing goes in parentheses and gets squared. We have to take the side of a square and square it to get the area of the square. Don't forget to multiply by the thickness of the cheese slice, the dx. So area times thickness makes volume. So this is us adding up infinitely many volumes. Final answer.